Okay, so we are starting on page 40 today, and we're going to look at some examples of interpolation and extrapolation, as well as interpreting the slopes and y-intercepts. So the same stuff that was in your notes video. So we're going to hop around a little bit because, again, in that notes video, we kind of hopped around. So we're going to scoop up the examples that we didn't do in your notes video. So starting on page 40. For this first example, it says exercise 5, but the first example we're going to do today, it says biologists are modeling the number of flu cases as it spreads around a particular city. We're maybe a little too familiar with examples of this type over the last couple of years, but it says the total number of cases Y was reported each day, X, after the first total reached 16. So they started counting when they got a total of 16 and they went from there. The data for the first week is shown in the table below, and we've got our number of days and our number of cases. The first thing we're going to do is use our calculator to find an exponential regression. So this tells me in the problem what type of regression to find. Almost always for the problems that you're seeing, it tells you what type of function that you want. So in our last few days, it said find the best fit line. That tells me I want a linear function. Here it says exponential, so we'll find an exponential function. So what I'm going to do is pull up my calculator, and I'm going to recreate this table in my calculator using a list and spreadsheet page. I'm going to label my columns as X and Y because that's how they're labeled on my paper. If you wanted to call them days and cases, that would be fine too. But I'm going to use X and Y to try and make this a little simpler on myself. And then I'm just going to type the X information in. Oops, no 2. We've got 3, 4, 6, 7. And then I'm going to type in the number of cases. 16, 18, 22, 25, 33, 35. Don't forget to enter after you type that last value in, and make sure that you're careful when you enter your information. As you guys saw just a minute ago, I went to type in day 2, but there is no day 2 in the table. So a lot of times if you get something incorrect in your function, or when you go to extrapolate or interpolate and you get something incorrect, not always, but a lot of times it's because you have some incorrect data in here. So correct the data and your function will update as well, but just be careful when you type your stuff in. Now that I've got my data entered in my table, I'm going to hit the blue control button and then the dot key so that I can add a data and statistics page. Again, I like to do this on a separate page so there's a little more space for that function. And then remember, you need to assign your variables. So down here it says click to assign. That's the x-axis. I'm going to assign x down there, and I'll assign y where I would expect the y-axis to go. And I've got a scatter plot here of my information. Now, I think it would be probably reasonable to say this might be a linear pattern here. It looks a little linear, but our problem specifically says to find an exponential regression. So I'm going to find an exponential function that fits this, but it does look kind of linear. So I'm going to go to menu and then down to analyze, and we've done this already in this unit, and then down to regression. And then I want to select exponential. So I'm going to go down the list. There's exponential, and I'm going to select exponential. So here I've got an exponential function that fits this. Okay. Go ahead and round to 2 decimal places for me. So we would get for our exponential function y equals 15.92 times 1.12 to the x power. There's our exponential function. I'll put my calculator down for just a second so you can see where I put that in my notes here. And then part B says, based on the regression equation, so using that model that we created, how many total cases of flu will there be after 2 weeks? So after 2 weeks, I have to translate into days because my X value is in days. So I'm going to plug in X equals 14, okay? Because I want it translated into days. So I'm going to pull my calculator back up here, and I'm going to plug in X equals 14 because it's 2 weeks. That would be 14 days, okay? And then I'm going to go to a calculator page to plug in that X value, or I could actually probably just pull the scratchpad, that'd be fine. So I'm going to use that model that we wrote down, so 15.92. And then, let's see, times 1.12. And then remember this little mountain looking guy? It's called the caret key that gets me an exponent if my exponent is not like a squared. And then since X is the exponent, I'm going to plug in 14 for my exponent. So we get 77.80, I think, if we rounded to 2 decimal places, so 77.8. So how many total cases of flu will there'll be? I'm going to say 77 cases, about 77 cases of flu. Okay, so I'm going to put my calculator away so we can look at it on the notes page. So 2 weeks would be 14 days. I have to use days because that's how this information is set up here. And when I plug in 14 for X in my function, I get 77.8, so about 77 cases. We're going to skip part C, and we're going to take a look at part D. Part D says hospital officials will declare an emergency when the total number of cases exceeds 200. On what day will they need to declare this an emergency? So number of cases is over 200. So that means my Y value is 200. So what I'm going to do is go back to my calculator here, and I'm going to go back to my document. Actually, we can do this on Scratchpad. I'm going to go to a graph, or you can add a graph page if you want. And I'm going to graph the function that we created. So 15.92 times 1.12, and then we want that goofy caret key again, to the X power. So I'm going to graph that. And then I'm going to hit the tab key, and I'm also going to graph 200. If this were a linear equation, I could plug in 200 for Y and solve for it algebraically. That's something that we know how to do. This is an exponential function. We haven't talked about how to solve exponential functions yet. You saw them last year in Algebra 1. We're actually going to take a deeper dive into exponential functions a little bit later on. But since we haven't talked about how to solve exponential functions yet, I'm going to use my calculator to help me here. So I know that I want my Y value to be 200. So I'm going to graph 200. And now I can see just a teeny tiny bit of my exponential function. I can't see the 200 at all. That's going to be way off my graph. So what I'm going to do is adjust my zoom here. So menu, window zoom, and I like zoom fit to start. I still can't see my Y. That's okay. I'm going to zoom out from here. There we go. Now I can see both my exponential function and my Y. If I want to know the first day that the cases will be above 200, I'm going to look for that intersection point here. So I'm going to go to menu, analyze graph, and we're going to look for that intersection. So I'm going to click on either side of where that intersection is. Remember, you're not trying to land on it. You don't need to do that. Let the calculator do the work for you. So that intersection happens on day 22, right? We're not yet to day 23. So I'm going to say after about 22 days. Okay. So I'm going to put my calculator down and jot down in our notes what we just did and what we saw. So I know that I'm looking for when Y was equal to 200. So I graphed this. And we saw we had an intersection at 22.3, I think, comma 200. So we'll say about day 22. On day 22, we hit that 200th case. So on day 22 is when we would need to declare an emergency. Questions for me for our first example on page 40? Okay. This would be extrapolation here because this is beyond the scope of my data. This would also be extrapolation because again, this is beyond the scope of my data. If we take a look at exercise 3 down at the bottom of page 40, we are looking at something similar. This time we're looking at cost per widget produced by a factory. It generally drops as more are produced, but then starts to rise again due to overtime costs and wear on the equipment. So there's sort of a sweet spot here for costs. If I'm producing only a few things, it's kind of expensive. If I produce a lot of things, it gets a little bit cheaper. If anybody's ever been in like a group or an activity or something and you ordered like t-shirts for your activity, if you only ordered a couple, it's a little more expensive. The more t-shirts that you order, that cost per shirt gets a little cheaper. It's because if they're gonna go through the like work of firing up the like printing machines and putting in your design, the more that they produce, the little bit cheaper it is on their end. It's kind of expensive to set that up initially, but as you order more shirts, they can distribute that cost over more shirts. But there is, again, like this sweet spot where if you order a certain amount of shirts, it's not that expensive. If you order like a zillion shirts, it starts to get pretty expensive because then you're looking at more time to be able to produce those things. So somebody has to make those shirts. So it costs more money because of the more like time effort that's involved. So we have that here with some widgets, and we can see our cost per widget versus number of widgets. And we want to go ahead and look at what type of model would be appropriate here. Now, if we read the problems, we already have a pretty big hint as to what type of model we're going to want. It says, why should a quadratic model be considered? Well, without even typing this information in, that kind of tells me I'm probably going to want a quadratic model, right? If I just read the problem. So let's go ahead and make our table for this and take a look at why that might be a good fit. So I'm going to pull my calculator back up. I'm going to go ahead and make a brand new document. If you wanted to, you could type over the old information that you have. I'm just going to go ahead and make a brand new document. So I'm going to go to my dot key here. No, I do not want to save this, but I do want to add a new list and spreadsheet page. And since I made a whole new document, I can call these X and Y again. If you didn't make a new document, if you just added a page and called these X and Y again, the values down here would autofill with what we had just called X and Y. So if you want to use the same variables, either you're going to have to retype the data or you're going to have to rename, or you're going to have to make a whole new document. So X values 35, 88, 110, 135, 154, 190. And then let's plug in our Y, 9.32, 2.63, 1.42, 1.32, 2.12, and 5.50. And we're kind of seeing that pattern here just in our values from our table. So when I only produce a few, like $9 and some change, when I produce a little more, significantly less expensive, I should say. When I produce a little more, less expensive, a little more, less expensive, a little more, it starts to get more expensive again. And then even more, that price starts to creep up a little higher. Now I'm going to go ahead and do Control Doc to add a data and statistics page so I can get my scatter plot. Again, make sure you assign your variables. I've got to assign the X down here and the Y along the side. If you try to find a regression without assigning your variables, that option is going to be grayed out. You won't be able to do anything because it doesn't know what's X and what's Y, what's on your X axis and what's on your Y axis. Okay, so looking at the scatter plot, why might we think quadratic? Yeah, it's got this sort of parabolic shape to it, right? It goes down and comes back up. Why might I think parabola? Because it looks like a parabola, right? And then while we're here, let's go ahead and find that regression. We're going to need it for part B, so let's go ahead and get it while we're here. So menu, analyze, regression, and then we want to show quadratic. Be careful, there's a little trap here. The thing that your pointer is closest to is a keyword, and we don't interact with that many keywords, so it's easy to pick this one on accident. Make sure you select quadratic, okay? And then we get our function here. So I'll worry about the function in just a minute. But I want to hop back to my notes so I can answer a couple of questions. Okay, so why should we select a quadratic model? Because our scatter plot has a parabolic shape. It has a quadratic pattern. The scatter plot has a parabolic shape, or it has a quadratic pattern to it. And then part B asked us to use our calculator to create a scatter plot of this data and verify its quadratic nature. We did that. And then we want to use that model to predict the cost of producing 50 widgets. Some of the text got cut off here, but what we want to do is use this to predict the cost for producing 50 widgets. So I'm going to jot down our function from our calculator. 0.01x squared minus, be careful with your signs on the regressions. It's always plus negative, so it's easy to skip over that something is negative. 0.25x. The next digit here would be a 0 that would not round up to a 1. So that's why I'm going to keep this guy at 2 decimal places. And then plus 16.863. I'm rounding to 3 decimal places for this problem because what we want to predict is a cost. Money, we round to 2 decimal places. I'm getting a 3rd decimal place here. That way I can see what I should round to when I round to the nearest penny. So there is a little method to the madness here. And then I want to know the cost for producing 50 widgets. So my X is 50. That's the number of widgets that I want to make. So I'm going to go back to my calculator and I'm going to plug 50 in for these X values. Okay, plug 50 in for my X values. And I'm going to do this just on a calculator page using the model function that I've jotted down on my paper. So I'm going to pull my calculator up here. And then I'll just pull up the scratch pad. We can do this on the scratch pad. Calculator side. So we've got 0.001 times 50 squared minus 0.25 times 50 plus 16.863. So I just plugged 50 in the X spot and we get 6.863. So $6.86 per widget is what this would cost. $6.86. $50 is within our collected data range. This is actually interpolation. Questions for me on this second example for today? Okay. These were the longer problems because I had to enter all this information into my calculator and find that best fit model. The next couple that we're going to take a look at are going to be find the slope or what's the y-intercept mean. So the last couple examples we'll do today will go by a little bit faster. Go ahead and turn the page for me. And we did example 7 in the notes video. So we're going to take a look at example 8 together. Example 8 says, what is the approximate average rate of change? So average rate of change means slope. Anytime I see average rate of change, that means I'm going to find some slope. Average rate of change in quiz grade between 3 and 9 absences. Okay, so I'm going to look at, it says between 3 and 9 absences. I'm going to look at the value for 3 absences and the value for 9 absences. Average rate of change here means sort of algebraically, we're going to find the slope. But in terms of this problem and what it is we're looking at how does my quiz grade change based on number of absences. Okay, so I'm going to find the slope between these two. So I'm going to do 60 over 9 minus 88 over 3. So I treated these like points. y2 minus y1 over x2 minus x1 for that slope formula. And then when I subtract, we would get negative 14 over 6. And when I divide, we get negative 2.3 repeating. So what this is telling me is that the more days that you miss, as you miss more days, 60 minus 88, oh, that should be 18. I think I had reduced this already. This should be, okay, 14 over 3. Sorry, guys. Because this would be 18, right? And then divide by 2. That's okay. I thought my notes didn't make sense there. Okay. So the negative 4.67 is what we should get. Thank you. So what we're looking at here is the score decrease on our quiz per extra day I miss between 3 and 9 absences. So we'll say you can expect your score to drop by 4.67, and it's dropped since we got negative 4.67. If this were a positive number, I would say my score would go up. You can expect your score to drop by 4.67 points for each day you are absent between 3 and 9 days. And I should put one little caveat in here. This is not exact. This is an average. So you can expect your score to drop by an average of 4.67 points for each day you're absent between 3 and 9 days. Maybe it's only 2 points for some people, maybe it's 6 points for others, but that's our average. Okay, so if you see average rate of change, slope. Okay, you're just finding the slope. Other questions for me? Okay, turn the page, and we've got one more example to look at together for today. So again, we did example 9 in the notes. We're going to take a look at example 10, but example 10 is the same type of problem as example 9. So example 10 says, which of the following is the best estimate for the average change in resting heart rate associated with a 1-hour increase in exercise per week? Okay, I see best estimate of the average change. So I know I'm going to find slope again. Okay, and then I want to give the best interpretation of the y-intercept. So what we're looking at here is number of hours that I exercise per week and my resting heart rate. Okay, presumably this is something involving cardiovascular activity, so that our resting heart rate would drop, because that's what we're seeing here. This trend here is that as I increase the number of hours per week that I exercise, my resting heart rate is going down. So if I want to estimate the average rate of change in resting heart rate, I need to pick 2 nice points from this graph and find the slope between them, right? This is just slope. We don't have a table this time, and it doesn't give me specific values like the last example did. So from my line, I'm going to find 2 decent points and find the slope between them. So I'm going to pick this guy. It's pretty close to halfway between 65 and 70 here, looks like to me. And it's on a nice line here. So I'm going to call this point 3,67. And then I'm going to find another point that looks nice to me. I'm going to use this point right here. That looks like it's right on the corner. I'm going to call this point 6, 55. 6, 55. That one looks like it's right on the corner. Again, you don't have to use the points that I picked. If you use different points than what I picked, again, just try to make this easy on yourself by picking the nicest points that you can, but your slope may be slightly different if you don't use the same points that I do. That's okay, it should still be close, but just make sure you are picking points from the line and not points that are off the line. Okay, I would get a very different slope if I picked these 2 points versus if I picked 2 points that are on or pretty close to the line. So I'm going to find the slope between these two. So 55 over 6 minus 67 over 3. So we would get negative 12 over 3 here, which would be negative 4. So this means that your resting heart rate goes down. Since this is negative, goes down. If it were positive, it would be going up. Goes down an average of 4 beats per minute for every 1 hour increase in exercise per week. The tricky part here is not finding the slope. I know you guys can find slope. We found slope for like a solid week and a half in Algebra 1 last year. I know you can find slope. The tricky part here is interpreting what this means, okay? So I found the slope between 2 points here. What I'm looking at is a reduction in my resting heart rate in beats per minute for every hour that I move over. So if I thought about what this means, if I say my slope is negative 4, that means I'm going down 4 and over 1, right? And the labels here make this a little tricky. So I'm going down 4 and over 1, right? From wherever I am on the line, down 4 and over 1. So that means that the 4 I'm going down is my resting heart rate in beats per minute. The 1 I'm moving forward is increasing that hours of exercise per week. Okay, and then the other part it wants me to interpret here is the y-intercept. So my y-intercept is here, just under 80. Okay, so my y-intercept, usually when I interpret, I like to jot down what it is first. I'm going to say that it's about 79 beats per minute. It's just under 80. So this means that if I spent 0 hours per week exercising, when you spend 0 hours per week exercising, your resting heart rate should be approximately 79 beats per minute. For whoever this person is, if they didn't exercise at all, we would expect their resting heart rate to be about 79 beats per minute. Questions for me? Okay, that's it for our notes portion for today. You do have 2 assignments on Khan Academy asking you to find the slope of the line of best fit, like we did here, and then interpret y-intercepts and slope, like we did here. So it's a little more similar to these last couple of examples that we've done, but that's what you have for today.